Welcome to ChemVid. Today we're talking about units and measurements. So how we measure and what units and what goes in a proper measurement. All that kind of stuff. Alright, so first of all on these notes, it asks you to find two different ways of measuring the volume of a water bottle. And a water bottle, a very common measurement is a liter water bottle or even a pint water bottle, quart, okay? So those are all different units to measure the same thing, volume. Whereas the size of a binder clip, that's a length. And so we're going to use inches or centimeters or meters or something like that. So whenever you're measuring something, the units matter because it tells the scientist what you're actually measuring, whether it's volume, size, mass, or whatnot. Okay? So let's begin. When we report measurements, they have both a blank and a blank. This is very important, and we talked about this earlier. When you have a measurement, you always need both a number and a unit. Okay? A number and a unit. Very important. And the reason why is, if you leave off the unit, then I don't know what the number means. 2, 3, 4... those are just counting numbers. I don't know, are they meters? Are they kilometers? Are they, elephants? So whenever you report a number, whenever you take a measurement, it is always important to have a unit as well. Number and unit. Do not forget. Okay, now for the next part of our notes, I'd like you to take out a ruler and measure the length of this piece of paper, your notes, okay? And I'd like you to measure it in centimeters and in inches. So go ahead, pause the video and do that. Okay, so when I measured it, I got about 11 inches and 28 centimeters for the long side of the piece of paper. And now in the notes, it asks, well, how many feet is that? And if you look at it, you can tell that it's not quite a foot. It's not quite 12 inches. But I'm not exactly sure how many inches it is. So this is the way that we convert one unit into another unit. All right. So I'm going to go from inches to feet. And I'm going to do it so that I show my work so you know exactly what I'm doing. Pay attention because this is how I would like you to show your work whenever you're doing unit conversions. All right, so I look at 11 inches. I write that down. I write my measurement down. I draw a line, and then I have a fraction over here. And I'm going to put inches on the bottom and feet on the top. Now, whenever you're doing a ratio conversion like this, you always put in how many inches equals how many feet, or how many feet equals how many inches. It doesn't matter as long as you're consistent. I know that there are 12 inches in 1 foot. So then I'm going to multiply by the top just like you would with a fraction, and I'm going to divide by the bottom just like you would with a fraction, and I'm going to get 11 times 1 divided by 12 is 0.92 feet. And the reason why a lot of scientists use this way and a lot of chemistry teachers use this way of teaching is because it helps you know whether or not you need to multiply or divide by 12, because sometimes my students get that mixed up. And in fact, I do too, so it's, no judgment. But it also lets you see, okay, inches divided by inches is going to equal 1. So see, your units cancel out, and then you're left with the units you want. That's how you know whether or not 12 inches goes on bottom or whether it goes on top. Because you always want to count out, you always want to get rid of the units that you start with in order to go the units that you need. In this case, that's feet, okay? Over here, 28 centimeters, go ahead and set this one up. Okay, go ahead and draw your lines and set it up and see if you can figure out how many centimeters, or meters, 28 centimeters are. Pause the video and try that out. All right, so just like before, I put centimeters on bottom because that's the unit I'm trying to cancel out. And then I put meters up top. In 1 meter, there's 100 centimeters. So I took 28 times 1 divided by 100, and I get 0.28 meters. So 0.28 meters is the exact same length as 28 centimeters. They're just measured in different units. And that's why units are so important, because it gives you an idea of what that number means. For those of you who didn't know that there were 100 centimeters in a meter, go ahead and scroll down on your notes to the bottom of the first page. And this prefix chart is here to help you. So centa, I find it right here, the prefix, centa. 1 unit is equal to 10 to the second centiunits. Okay? And what that little 2 means is how many zeros there are. So basically, this is saying 1 meter is equal to 1 with 2 zeros after it, or 100 centimeters. And so whenever we're trying to do conversions between these different prefixes, this is how you know how many prefixes are in one base unit. All right? If you look up at the top, there are negative exponents. All that means is that you need to put zeros in front rather than behind. All right? So that is prefixes, and that is how we do show our work and do these kinds of conversion problems. All right, this next part, they're called SI base units, and this is the system that we use all over the world for our units. So for instance, time, whenever we measure time as scientists, seconds is our unit. Meters, kilograms, Kelvin, mole, and amps. So moles and Kelvin might sound a little weird to you, but don't worry, we'll go over them. And then we would never use feet or pounds or ounces or anything like that, because those aren't the international units that we use. This is so that we can talk to one another and speak as scientists and check each other's work. So that is what an SI unit means. All right, down here, what unit would you use to report the length of a classroom, and what unit would you use to report the mass of a stapler? Go ahead, take a moment, and write down what you think would be the proper unit to measure these guys. All right, so in my personal opinion, I would measure the length of the classroom either in meters or kilometers. Meters is probably the best bet, because a kilometer is more like a mile, okay? And my classroom isn't a mile long. So meters, that's going to be more acceptable for measuring a classroom. Meters are more like yards, okay? And that's what I would use, and that's why I would use it. A stapler, I would use grams. Again, kilograms are more like a pound, okay? And a stapler definitely does not weigh a pound. So I would use some grams to measure that. And the grams are smaller than a kilogram, but it's enough that I would be able to measure my stapler. All right, next thing, big and small numbers. So the distance between Jupiter and the Sun and the diameter of a helium atom. 788 billion meters is how far Jupiter is away from the Sun, okay? But this number is so big, it would be hard to write. I would be writing that number a lot. And there's room for error because I might transpose it wrong, I might write it wrong, or I might forget a zero or whatnot. So scientists have 2 ways of making big numbers easier to write. And the first one is called scientific notation. And so scientific notation is where we use bases of 10. We count the different places and put them in. So what we do is we start off at the decimal. So here I have a decimal. And I count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay? And for scientific notation, you always stop the decimal when there's one number ahead of it. You always want one number ahead of it, not a 0. Okay? So then I would write out 7.88 times 10, and since I moved over 11 times, I put a little 11 here. Because what this notation does is that it actually counts how many places you moved over, and then you can move it backwards once you know the places. And then before I'm done, I must put in my units, because a number without units is not good, and you will lose points because you need to know your units. You must be precise when reporting numbers. All right, so that's scientific notation. A little hint, whenever you have a big number and you're moving to the left, okay, the decimal point is moving to the left, and it's a big number, your exponent will always be positive, okay? And that's just how it works. All right, let's try a little number. Little numbers work the same way as big numbers. They're far too hard to write, and they're kind of really hard to say, especially when they're small like this. So what I'm going to do is I'm going to do the exact same thing. I'm going to take my decimal point, and I'm going to count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And do you see how I stopped when there was one number in front and it wasn't a 0? That's how you know when to stop. That works for both forward and backwards. So then I'm going to write 1.4 times 10 to the negative 10th. And the negative means that I move to the right. I have a really small number. So whenever you look at scientific notation, if it has a negative sign, that means it's a small number. And if it's positive, then that means it's a big number. So whenever you move to the right, whenever you move your decimal place to the right, that means it's a little number. And you're going to have a negative exponent. Okay? And before I forget, I'm going to put units on this guy so I don't have any naked numbers. Always clothe your numbers. Okay? All right. So that's the first way that we do it. This is called scientific notation, and it's used a lot, especially when we start getting down to small things like particles of light and light waves and how big an atom is, okay? As you can see here, 1.4 times 10 to the negative 10th, that's how big a helium atom is. So we get into some pretty small numbers, and knowing how to do scientific notation really helps. All right, the next way that we do this is with prefixes. So prefixes are on your sheet at the bottom. All right, so whenever you're dealing with prefixes, I suggest you have this little reference sheet with you because it'll help you out a lot. So prefixes, what they do is they take the place of the zeros. So let's go back to my example. Distance from Jupiter to the sun, okay? And so now what I'm going to do, I'm going to actually count how many zeros. So here's 3 zeros, 6, and 9. So then I go back to my reference sheet, and I find where there are 9 zeros. So if I look, 3, 6, 9. So this would be a giga. Now instead of writing a giga, what I'm going to do, or instead of writing 9 zeros, I can write 788 gigameters. And see, that giga takes the place of the 9 zeros, and that way I don't have to write them all out every single time. Go ahead and try this one on your own, the small one, the distance of a helium atom. All right, so when I looked at my chart, a nanometer had 9 zeros, and they were small. So I could do 0.14 nanometers, or I could add another 0 to the end and do 140 picometers. And as you can tell, this makes things much easier to write, and you don't have to keep writing out zeros. Okay, Practice the 3 questions before class, and I will see you later.